Let us now talk about the saturated liquid and the vapor states. Now, if you look at this table over here, you have a fixed value of temperature, with respect to which you have the value of the saturation pressure, and then you have the value of the volume or the specific volume of the saturated liquid or the saturated vapor state. Okay. Now, in this table, if you have to denote it, this column represents the temperature of the state of the system. This column, it represents the corresponding saturation pressure. Now, why I say corresponding is because this pressure is corresponding to this temperature. Alright. Next, in this column we have the specific volume of the saturated liquid, and in this we have the specific volume of saturated vapor. So if you remember the temperature volume diagram of a pure substance, so as you keep on increasing the temperature, the saturated liquid volume, it starts to increase a bit, but the vapor volume, it starts to decrease, because the horizontal line, it starts to, or the length of the horizontal line, which is joining these two states, it starts to decrease. So I hope you can see a correlation of the graphical analysis with this tabular form of data. Now, every liquid property will be given with the subscript F, and every vapor property would be given with the subscript G. So Vf is the specific volume of saturated liquid, alright, and the value of, or you can say the specific volume of saturated vapor would be Vg. Specific volume of saturated vapor is Vg. Now, we all know that there is a certain amount of heat that goes into when we go from liquid to vapor form. Alright. So whatever the difference that we have between Vg and Vf, this is known as Vfg, and this is called the enthalpy of vaporization. The enthalpy of vaporization, or latent heat of vaporization. Latent heat of vaporization. Okay. So wherever you see Fg in the subscript, it means that we are talking about the latent heat part. Alright. So this is a very important term to understand, because this is what you will be tackling in the questions on such topics. Alright. So this table is something that you will encounter a lot in the questions that you get on this. Now, what does this enthalpy of vaporization or the latent heat of vaporization representing? It is representing the amount of energy which is needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. Alright, and it decreases as the temperature or the pressure increases, and it becomes zero at critical point. So if you remember that TV plot, alright, so this is the volume and this is the temperature. So this is how you used to have that plot. So the length of this line is basically giving you the enthalpy of vaporization. Okay, so as the pressure goes up or the temperature goes up, and you know that your lines, they keep on getting shorter, the horizontal lines. So this enthalpy of vaporization, it keeps on decreasing, and as you approach the critical point, it becomes zero. So now let's continue to the next portion. So we have a pressure or temperature axis over here and a volume axis over here. Now during a vaporization process, a substance exists as part liquid and part vapor. Now it is a mixture of liquid and vapor, which can be represented on this particular graph. So you have your critical point over here. So this is the Cp. Alright. and these lines, so you have a curved line towards the left of the CP, and then you have a curved line towards the right of the CP. Towards the left, it represents the saturated liquid state. So any point on this line would indicate a saturated liquid state. Alright. And any point on this curved line would indicate a saturated vapor state. A saturated vapor state. Alright. Now, this means that when you are in this region, that is the vapor and the liquid mixture region, in this region, okay, you have part vapor and part liquid. So this mixture should be analyzed properly. Okay, to do this, or to analyze this mixture, we need to know the proportion of liquid and the proportion of vapor mixing. Now this is done by defining a new property, which is the quality of the mass of the vapor to the total mass of the mixture. So that is also known as the dryness fraction. Dryness fraction. So let's take the case of steam, and this becomes the dryness fraction, or the quality of steam. The quality of steam, and it is denoted by the letter small x. Alright, and the mathematical definition is the ratio of the mass of vapor, alright, divided by the total value of the mass of the liquid and vapor mixture. Okay, so if you look at the value of total mass, this is equal to the mass of vapor plus the mass of the liquid component. Alright, so you can write it down like this. It becomes mg plus mf. So the value of x becomes mg divided by mf plus mg. So this is the value of the dryness fraction or the quality. Now if you look at this diagram, which is the P or TV diagram, alright. So when you are at this line at any state, okay, when you are on this line, you know, at this line you have a total liquid state. This means there is no vapor component. So which means that the numerator would become 0. So the value of x is 0 at the saturated liquid state line. And if you are at this end, or at this line, on this line there is no liquid. There is no liquid. So mf would become 0. This means this value would become 1. So this is the least value, and this is the most value, or the maximum value. So this gives us a conclusion that the value of x, it would lie between 0 to 1. 0 on the saturated liquid line, and 1 on saturated vapor line. Alright, so this is a very important conclusion that has come to our knowledge. So now let us look at this diagram, which is a two-phase system. So let us say you have some saturated vapor, alright, and let us say the volume of this is Vg, and then we have some saturated liquid, and the volume of this is Vf. So when you combine it, you get a saturated liquid vapor mixture. And let us say the volume of this is some average value. Okay, so we have this tank in which you have some saturated vapor at some volume, and you have some saturated liquid at some volume, and when you mix both of them, you get a mixture of saturated liquid and vapor, which is at an average volume, let us say, of the two volumes which are for gas and vapor. Okay, so the total volume of this container, let us say, is V. So this is the total volume, which is Vf plus Vg. Now these quantities are total volumes, not specific volumes. So this means that V is equal to small m into small v. Okay, and this would be the total mass and this would be the average volume. So this becomes m total into average specific volume is equal to the mass of the liquid into the specific volume of liquid plus the mass of vapor into specific volume of vapor. Alright. Now, the value of mass of fluid, let us say, can be found out by the total mass minus the mass of the gas, isn't it? So this equation would become mt into V average is equal to mt minus mg into Vf plus mg into Vg. Alright, so you divide the whole equation by mt, you divide it this side by mt, this by mt, and this by mt, that is the total mass. So now you can cancel off mt and mt from here. Alright, so you get V average is equal to 1 minus the mass of gas upon the total mass into the specific volume of liquid plus mg plus mt into the specific volume of gas. Now looking at it in a very careful manner, this fraction gives us the quality of steam, that is X, or the dryness fraction, and this is also the value of dryness fraction. So the whole expression would now become the average specific volume is equal to 1 minus X into the liquid specific volume plus X into the vapor specific volume. Now if you expand it a bit, you will get Vf minus X into Vf plus X into Vg. You can combine the values of these two terms and we will have V average is equal to Vf plus X into Vg minus Vf. Now the value of Vg minus Vf was the enthalpy of vaporization, that is Vfg. So this would become Vf plus X into Vfg. So this is an important relation to note down. And taking this equation a bit further, I can say that the value of X would now become average specific volume minus Vf upon Vfg. Alright, so this is something that we get. Now based upon this equation, let us draw one more diagram to represent it on a graphical level. So let us say we draw such a diagram. So this is volume, this is pressure or temperature. Okay, so let us say this is the kind of graph you have, and we have a point over here which is A, and let's draw a line which is, so this is point B, or I would say point C. Let us take a point B somewhere in the middle. Okay, so in this we have this process which is given to us. Now point A is a saturated liquid state, so this can be taken to be as Vf, and C would be taken to be Vg. Let us say when you combine both of them, you get something which is Vfg, or I would say not Vfg but V average. Vfg is this, the difference between the gas vapor volume and the liquid volume. So this is V average. Alright, now to find out the value of X, I need to subtract V average with Vf, and when you do that, okay, so this is from origin. If you take the values, so from origin, this is V average and this is Vf. So this value, this line this line is giving me the value for V average minus Vf. So this particular expression is equal to the length AB. Alright, and VFG is the complete distance, or the complete you can say difference between VG and VF, which is this complete line, which is AC. So VFG is equal to AC because it is equal to VG minus VF. So I hope you understood this. So the value of X from graphical analysis would come out to be AB upon AC. So this is how you can use a pressure volume or a temperature volume graph to find out the value for the dryness fraction. Alright, similarly you can use this particular formula to find out the specific the specific enthalpy as well. So you can have you can say H average is equal to HF plus X into HFG. You can have you can say internal energy specific value. You will have U average is equal to UF plus X into UFG. So these these expressions can be used to find out the property at some intermediate point, which is between the saturation points of liquid and vapor phases. So I hope you understood the procedure to find out the value of enthalpy, the value of internal energy, the value of volume at any intermediate state which is lying between the saturated states. Okay, so with this video we finish the whole theoretical concept of the properties of pure substances. Now we look at some question solving videos on the same topic.